All right. Hello, everyone. I can see some of you, I think, sitting right down the middle. So you guys can wave and whatnot. Okay, so this is me. I'm Greg. Yeah, there's a picture of me because I'm not on video. And, well, you don't want to see me at 8:30 in the morning. So um, I am the CEO of a small company called Singularity. And Singularity, the purpose of that is basically to maintain the open source software of Singularity and make sure keep it open, keep it free, and available. Additionally, I'm a senior architect to a new company called RStore. You won't find much about RStore, so if you haven't heard about RStore, don't worry. It's because we're in stealth mode and we haven't made any big announcements yet. So you should start hearing things, well, I don't want to say shortly yet because we're still working on a bunch of stuff, but hopefully in the future you will hear a lot about us. And additionally, I'm a scientific advisor to Lawrence Berkeley National Laboratory, which is a UC Department of Energy, US Department of Energy and UC managed national lab. And I've done some open source work that I'm pretty well known for. I've founded a small Linux distribution called CentOS Linux, if you guys heard of that. I founded that in 2002, 2003-ish. I also founded, and I'm still the project lead of a cluster management solution called Werewolf, and a technical steering committee for something called Open HPC, if you've heard of that. But most recently, and what we're going to talk about today, is I am the founder and I'm the project lead of a container system called Singularity. So throughout my presentation, I've embedded a few different quotes. So this one's from the Pasteur Institute. And I like this one, of course, because, 3 of the projects that I've created are being referenced in one quote. And so this is really good for my ego here. So I put that, just to get me going for a presentation. So Singularity, Werewolf, and CentOS, winning combination. Okay, if you're not familiar already, this is a container. Now, I believe you guys have already been talking quite a bit about containers for the past few days. So you should be pretty familiar with the idea of containers. Now, one thing I do want to mention is that the enterprise industry has really made containers a household name in the computing industry. And one thing I want to add to that is that the use case of enterprise computing is not the same use case that we're looking for scientific computing. Now, I'm not going to spend a lot of time on that, but I'm happy to answer questions afterwards. But I do want to use that as a segue to talk about what is it that containers are providing to us, to scientists. So first off, reproducible software stacks. Now, when I say that, what I mean is a scientist can come along and they can build a particular application. They can put it inside of a container and know that they can come back to that container at a later date or on a different system and know that they're going to get the same results. And that leads into computing mobility or agility. That is the ability to run that workflow, that container, anywhere and know, again, you're going to get the same results. And this leads into the ability to distribute your work and let your peers validate your work and expand upon your work. And this also gives a reasonable escape from something called dependency hell. If you're not familiar with dependency hell, then consider yourself extremely lucky. In a nutshell, it's when you go to install an application, that application requires 5 other applications, and each one of those applications requires some other number of applications as well to be installed. And lastly, this gives you control of your own environment. So here's another quote that I threw in here from Washington University, is that users have been asking for containers for years, but always resisted. Singularity addressed the majority of these complaints, and it couldn't have been easier to install. Okay, so let's talk a little bit about reproducibility. And if this is stuff that you guys have already discussed, I apologize. We're going to go through it pretty quick, and then we'll get into some more technical stuff and talk about the future of Singularity shortly. So in science, reproducibility is of the utmost importance. Now, if you don't have the identical environment that a particular application or scientific workflow was developed in, you end up pretty much having to reinvent that environment from scratch. Sometimes the software environment is difficult, and other times it's actually impossible to recreate it exactly. Although sometimes you can get pretty close. Although validation that you're pretty close can also be a tricky problem to solve. But even when you get extremely close, you can see that you're not always going to have exactly the same environment. The Van Gogh on the left is obviously not worth the Van Gogh on the right. As a matter of fact, the Van Gogh on the left is not a self-portrait because he doesn't really look like Van Gogh. But it's a great painting, don't get me wrong. So if we take that metaphor a little further, if we're able to containerize the Van Gogh on the left and get a bit for bit identical copy wherever we bring it, now that is true reproducibility. That's what we're going for here. Here's another quote from the University of Chicago. Singularity allowed us to use software that was otherwise impossible to install under Scientific Linux 6, such as TensorFlow. And Singularity to the rescue. So now we're going to get into a little bit more detail about Singularity. Army Research Lab says that Singularity is the best option among the big three considerations for HPC. When they're talking about the big three considerations, I believe they're talking about Shifter, Docker, and Singularity. So moving on, Singularity was originally developed from necessity and demands and threats and bribes. And this comes from the fact that Docker has been around now for about 3.5, 4 years or so. And scientists have jumped on that Docker bandwagon because it seemed to have solved a lot of those problems that we talked about earlier. And as a result of that, when scientists are able to install Docker and run it on their laptops and their resources, they want to also run it on the HPC system. So when they turn and look at the resource providers and they say, hey, you know, Docker's working great for us, can you go and install it on our HPC systems? And the HPC admins are basically saying, no, it's incompatible with their workflow. It doesn't matter to them. So they just know that they want to have these sorts of features. And after a number of years of basically saying no to them, we can't do this, I did something which is kind of a novel idea for resource providers, which is to talk to the users and to find out what it is that they actually need. And what we found is that they're not looking to necessarily install Docker, quote unquote, on our HPC resources. What they're looking for is they need a solution for reproducibility, for mobility, agility, portability, and ease of use. Man, that's a lot of abilities. But basically, that's what they're looking for, these sorts of things. And from an HPC provider perspective, we're looking for something that has seamless integration with other HPC software and architectures. This includes things like resource managers, MPIs, InfiniBand, parallel file systems like Lustre, GPUs. And to do this, we need to limit the user's privileges and security context and their access to data. And once we do this properly, we can appropriately blur the line of what is isolated and what is not isolated. And what this allows us to do is to give users full access to all of the resource on a compute node while they're in a container. Additionally, we learned that the best way of managing container images from a scientist or a researcher's perspective is to basically manage it the way that they're currently managing all of the data that they already have. Whatever model they have for managing and dealing with their data, if the container is just another single file within their load of data, that is the best mode of operation for them to deal with their containers. And this has a few really cool caveats. I'm not going to spend too much time talking about performance of container images versus sitting on direct files or on a network-based file system, but it is highly optimized, especially if you're dealing with a parallel file system. So if you're running your container from a parallel file system as a Singularity container, it's incredibly efficient. Additionally, scientists can deal with it like they deal, as I said, with all just changing the POSIX permissions. Everything okay, you guys?
Yes.
Okay. So you can change your container just by basically changing the POSIX permissions or changing access to your data by the POSIX permissions. You can email your container. You can upload it to Google Drive if you want. But the most important thing here is that we're also controls compliant. Now, I don't know if anybody here has to deal with the issues of controls. I know in the US, we have a variety of different types of controls. These include things as easy and simple as export controls, all the way through HIPAA controls, through through top secret, through classified information, through through trade secret information. So there's a lot of different controls. And the nice thing about having everything in a single container image is that your environment, your container, you can manage in exactly the same way that you're currently managing all of your other data that you know how to do. So basically, again, it's just another file. And lastly, we needed to be Docker Hub compatible. And this is because there is a massive amount of research that has been uploaded and put into Docker Hub at this point. And we want to make sure that all of that research can be leveraged natively with Singularity. Ruger said that Singularity is used to get around glibc version requirements for binary distributions of the NCI GDC download tool on CentOS 6, as an example. All right, so let's move on. How do you create a new container? Well, with Singularity, it's basically a single command. Singularity create, and you point it at an image. That will create an empty container of a default size. And once you've done that, you can simply fill up that container. You can basically take something out of Docker Hub, which is what this command is demonstrating, and basically fill in that container with everything in the CentOS latest Docker Hub repository. And we'll get into more details on this in just a little bit. Additionally, you can bootstrap. The process of bootstrapping is installing or creating a new operating system based on a recipe file that you have set up. So in this particular case, we're starting with CentOS, and we can install everything from TensorFlow, OpenMPI, OpenFOAM, NumPy, anything you want into that container file. And once you've got that container file done, and it's exactly the way you want it, the whole point of this is mobility, that you can take that same file and you can copy that file to any other host or resource that has Singularity installed. This can be either, standalone systems, it could be HPC systems, or it could be cloud systems like Exceed or Amazon Web Services. Penguin Computing on Demand also supports Singularity natively at this point. University of Michigan, Singularity is a fabulous tool for providing forward and backward software compatibility on clusters for reproducibility. There was one thing I wanted to mention on the previous slide that I'll just do it real quick. One of the nice things about using, again, a single file image is that you can checksum that image and make sure that everywhere that you're copying it, you are in fact running the image exact bit for bit that you are expected to be running. So real quick, just go over installation. If you've done a configure, make, install, this probably is not going to be any more difficult. Once you have Singularity installed, you can do an initial test drive where you can basically run containers directly out of Docker Hub. So you can do a Singularity shell, and point it at Docker, and you're going to basically end up inside that container. And you can do this as a user on an HPC system that just already has Singularity installed. And you can point it to any Docker repository. If you want to import, this is again using the previous example, you can basically create an image and then you can import and fill that image up with something from a Docker Hub repository. And you can also pull images out of Singularity Hub. Now, there's two ways of doing that. The first way demonstrates pulling it out by name, and the next one is pulling it out by identifier. The point of Singularity Hub is basically to create containers via a workflow. And it's basically a platform for creating containers and then sharing those containers in a manner which is supportive of how scientists are publishing their work. The idea is that you can now take a Singularity Hub identifier, put it in your scientific publications, and know that anybody who wants to recapitulate your work can basically put that URL inside the container, and it will automatically run the workflow that you basically defined for your publication. The way that it works is basically it starts with GitHub. If you've heard of GitHub, awesome, you should. I mean, all the cool kids are doing it at this point. And basically what you do is you create your GitHub, you have your GitHub project, and you put a Singularity file in that GitHub project. And you then log into Singularity Hub, you set up your account, and you link that GitHub repository to Singularity Hub. Now, the Singularity file that you're going to create is basically the bootstrap definition or the recipe for how to create that container. Now what you end up with is every push to your GitHub repository will basically invoke a continuous integration with Singularity Hub, and we'll automatically trigger another container build or new container build, and we'll post it to Singularity Hub and then make it available for your citations of inside of your publications. Once you've created a container, we'll get into this a little bit more detail shortly. Once you've created a container, you can click on any one of these. Let's click on the top one, for example, and it shows you all the different builds that we've done on behalf of this particular container. And you can click on one of those and then click on the commands, and you can see these are the commands that I demonstrated earlier, where you do a Singularity pull and it basically goes and grabs that image. And then you can run that image in the exact same way as you do before. If we click on the build spec here, you'll see there is the Singularity file that I was referring to just a moment ago. And this basically is the Bootstrap definition, the definition file. So let's talk a little bit more about that. Starting at the top, the Bootstrap definition file basically has a header, and this header defines what your base operating system definition is going to look like. So for this particular environment, we're going to start with Docker, and we're going to pull out of Docker Hub the latest version of Ubuntu. Once that's been done, it jumps into the post section. The post section will basically do an apt-get update, and we'll then do an apt-get install Python pip and the locals. Once Python pip has been installed, we're going to install ASCII enema, and then we're going to do a local generation for ENUS, because everyone's in the US, right? No, okay. Once we've done that, we're going to set the environment, and in the environment, we're going to basically specify the locale that we defined, and then export that out. And then when this container runs, we're going to exec ASCII enema, and then basically pass any arguments. If you're familiar with shell lingo, you're going to see that that's how you pass arguments into from one program into another, or one script into another. Okay, moving on, just to give some demonstration and comparisons. This is a RHEL, or a YUM-based Bootstrap definition, and you can see the header's a little bit different. And then we basically just do the post is exactly the same, except for now we're sitting in a YUM-based system. And the run script that we're gonna do is basically just a hello world, and we're gonna print out our arguments after the hello world. Here's the same thing for a Debian or Ubuntu system, and just to give a comparison, header looks a little bit different. The post basically is now referencing apt-get instead of yum, and again the run script is hello world, and we're gonna print out our arguments. And again, just notice the run script. I'm gonna come back to that in just a moment. So this is what it looks like to actually build that container now. We're going to do a Singularity create pointing at that image, and we're going to do a Bootstrap utilizing that container, that def file. And if we do a, this is basically what it looks like when you do a shell. So if you do a Singularity shell pointing at that image, you're going to get an interactive shell prompt from within that image. And if you do an apt-get version, you're going to see this is basically the apt-get that we're running from within that container. If we do a cat etc Debian version, you'll see we're running 8.7. Exec is basically from outside the container, we can execute any programs inside that container. So in this case, Singularity exec pointed at the container. The cat program that's running is running from within the container, and we're going to be referencing a file that exists within the container. So again, cat etc Debian version 8.7. And then we're going to basically do we're going to basically call exec Python. Excuse me, I skipped one. I had a pop-up window come up here, and it covered this window. I'm not sure if you guys saw that. Hopefully not. Don't worry though, it wasn't really embarrassing. Okay, so the next command, we did a Singularity exec, and you can see just by changing the image, now we're doing a cat etc Red Hat release, and just by changing that image, that file, we're basically now to switch between operating systems with one command. So we can switch between Debian and CentOS, basically just, again, by referencing a different container image. If we do a Singularity exec Python, we never installed Python into this container. So the next command is a demonstration of how you would install something into a command into a container. So basically, we're going to do a sudo Singularity exec. We're going to make that container writable, and we're pointing at the image, and then we're going to do an apt-get install Python. If you're familiar with Debian or Ubuntu, this should be a pretty standard stuff. And then we're going to redo that command we did before, Singularity exec Python, and now it works. Okay, now we're going to talk about the run. So earlier in the Bootstrap definition that I mentioned, I called attention to the run script. This is what gets run or executed when you call Singularity run. And that is a standard shell scriptlet. So you can actually put anything you want in there. It could be a whole workflow definition if you want. In this particular case, we're just going to do a Singularity run pointing at the image, and you can see hello world. If you remember, any arguments that get passed will also get passed to the run script, and I'm passing that into that echo command. So now we can see if we do Singularity run pointing at the image and do testing 1 2 3, we can see we have now hello world testing 1 2 3 because those arguments were properly passed into that run script. If we do an ls -l on the container, you will see that the container is in fact executable. That implies that yes, you can actually run the container directly. So if we run the container in the next line by pointing it to the full path, temp debian.image, and then give it a couple of options, you can see it is running that predefined workflow as if it were a standalone program or a binary. There are some people that have actually done some really cool things by creating, for example, the latest version of Python or the latest version of TensorFlow and creating containers, having the run script execute those programs, and then they simply copy the container to the user's path. And then users can basically run that container like any other program on their system without even realizing that they're using a container. All right, we're going to get a little technical for a moment. We're going to talk a little bit about what happens for the process invocation. So starting from the beginning, the command Singularity is invoked. The first part of Singularity is basically going to go through a little bit of some shell code. It's basically going to evaluate what is the verb, meaning what is the action that we're doing, and what options need to be set. And that shell code is going to build up the runtime environment, or at least the shell-based runtime environment, for the backend Singularity binary. And that's going to be executed via the exec system call. Now, I don't know if everybody here has a background in programming or knows the difference between exec and something like fork. So real quick, I'm just going to give a little bit of background. Exec is a really cool system call because it will replace the process that is calling exec with the process that's being execed. So let's say, for example, the program that you're currently running has a PID of 100, and you exec another program from that PID of 100. The program that spins up is going to also have PID of 100, and the previous program you were running was going to go away. Now, this is one of the cool aspects of exec. So moving on now, the backend binary code, which has just got execed, is going to create the Linux kernel namespaces. And which namespaces that are created is dependent on what it is you're trying to do. By default, Singularity is going to try to separate out the fewest amount of namespaces as possible, because the more namespaces you separate, the greater the isolation you're getting from your host. And again, in high performance computing and in scientific computing, we actually are not going for isolation. We're actually going to blur the line between what is on the host and what is in the container. So the namespaces that are chosen to be separated are going to be separated based on a conditional. The Singularity image then is checked, it's parsed, and then it's mounted in the clone newns namespace. Bind points, additional file systems, and any other hooks that are necessary into the host operating system are set up at this point. And Singularity then calls exec itself again. And it calls exec on the appropriate process within the container that we just set up. Now, this is really important because Singularity has just execed itself out of existence. There's no more Singularity process running on your system. The only process that's running on your system, because we've execed Singularity again out of existence, the only process that's running on your system is the process that exists within the container. If you do a PS tree, you will see that this is in fact true. This means that the container process itself is going to run in the foreground, and it's going to have the same PID as the original Singularity process was given. Now, again, this is really important, especially when we're talking about resource managers and integration with resource managers, because this means that the process chain is exactly where the resource manager is going to expect it to be. And then when the contained process exits, the kernel is going to automatically clean up all of the namespaces that are associated with that particular process. And all those namespaces are going to collapse. And what basically is going to happen is it's going to collapse, leaving a completely clean system, just like Singularity was never there. So in a matter of speaking, Singularity then just is a bootstrap system to run a container. And once the container's running, it actually kind of leaves the building and it goes away. All right. Now, I don't know if we have any system providers in the room, but I do want to mention that knowing that users are, well, untrusted from a resource provider's perspective, and knowing that the containers that they want to run are also untrusted, which makes it a very different use case than pretty much every other container system out there. You basically have to give somebody the control, and you have to allow somebody the ability to control what's going to happen and what the users are allowed to do. And in this particular case, that's the system administrator. And the system administrator, via the configuration file, the Singularity configuration file, which must be owned by root, basically grants power to the users and specifies what the users are allowed and are not allowed to do. And it also allows you to do things like system-specific bind points. So if you know that your resource always has /global enabled or /scratch enabled, you always want that inside the container. So here you can specify a bind point, which will automatically and always make sure that that mount point exists inside your container. Again, we're blurring the line between what's contained and what's not contained. And again, on the resource provider perspective, the security model is very interesting about Singularity. And this is because the user contexts are always completely maintained as the container is launched. So this means that if I'm going to launch the container, me as a user, my username is typically GMK. So if GMK is going to spin up a container, I know that I'm going to be me inside that container. But more so, every escalation path that exists for me once I'm in the container is going to be blocked. This means if you want to be root inside the container, you must first be root outside of the container. All right, so let's take a look at what this conservation of privilege is. So again, at the top, who am I? I'm actually GMK. If I do a Singularity shell pointing at the image and do a who am I, you'll see I'm GMK. Now, I've been doing systems for a little while. I'm definitely not great at it, maybe, but I know how to install sudo. So we can assume I installed sudo properly. So sudo who am I? You'll see for some reason sudo is not working and it doesn't know why. So it's erroring out and it's giving a canned error message on why it's not working, but it doesn't know why it's not working. But it did get blocked. So I'm not allowed to utilize sudo. Even if I installed it correctly and gave myself rights to sudo, I'm not allowed to use sudo. And if I do an ls -l on sudo, you will see, yes, it is in fact set UID root. Everything should be working just fine. If I type sudo singularity, meaning I'm first root outside the container, sudo singularity exec, and then type in who am I, then I get the appropriate result. This would be the exact same block that would be in place if I happen to know root's password. Or if I happen to install a user space library inside the container that has a known exploit, like a glibc bug. So if I have a glibc bug inside of the container, Singularity is going to block any escalation path from that container or inside that container. So in a matter of speaking, we're even protecting ourselves. We're even adding layers of additional security because you're inside of a container. The only thing that Singularity will not stop you from is an exploit which exists on the host kernel. Now, that's an exploit that basically, because a container shares the host kernel with the host, any host kernel exploits will be able to be exploited, whether you're in a Singularity container, whether you're in a Docker container, or whether you're directly on the host. So there's no container that will protect against a kernel exploit. Well, obviously, depending on what that kernel exploit is. But any user space exploits that can be brought in with the container is blocked. So knowing that the user contexts are always strictly maintained and enforced, this means, again, I'm going to go back to what I keep harping on, we can blur the line between what is contained and what is host. And this means that the host and known resources are just as tangible. You can reach them just as easily when you're inside of a container as you are when you're outside of the container. Now, this facilitates things like obviously hitting devices directly, like NVIDIA or GPU devices, InfiniBand devices, etc. File systems and paths, network, X11, etc. And this is one of the things that allows containers to run so appropriately on HPC resources. Okay, I'm going to go through a few commands real quick here and just explain what they're doing, just to kind of give people a little bit more depth knowledge about what Singularity is doing and what it looks like. We've already gone over the who am I. So the top one, Singularity exec, point at an image. Who am I? I'm going to be the same user inside the container as I am outside the container. If I do a PWD, you're going to see I'm in the same directory inside the container as I was when I started outside the container. If I do an ls-l, you're going to see the same files inside the container as you were outside the container. If I go to touch a file in my home directory or create a file in my home directory, this is going to work as expected. If I do a ps-auxf, you're going to see all of the processes on your host are also going to be seen and visible from within the container. If I use the PID option, this is also the -p option. This separates out the PID namespace. So if I do a ps-auxf with the PID option, I'm only going to see the processes that exist inside this container. And the first process inside that container is going to have a process ID of 1. If this was an interview, I would ask everybody what has the process ID of 1. And if you don't tell me a NIT, you wouldn't get hired. So make sure everybody knows that. It's important. The PID of 1 is a NIT. So the PID of 1 inside this container is basically going to be a Singularity process, which is going to maintain that namespace. If you type in Singularity shell bind, this will take a host-based location and put it inside the container. So if we take /user from the host, we can now mount that or put that inside the container at /user_host. It probably wouldn't be a good idea to put it right at user because you may end up breaking a whole bunch of binary dependency. Singularity doesn't block for things like that. So careful because you can shoot yourself in the foot quite easily. Singularity shall contain, and then pointing at that image, will now all of a sudden make all of those locations that are on the host and all those blurred lines go away. So now all of a sudden, you're basically going to be sitting in a temporary volatile home directory that's empty. You're going to be, if you look at temp, if you look at var temp, you're going to see those are also empty. You can write to them, but as soon as you exit the container, all of that goes away. If you specify the home option, you can virtualize your home directory. This is important if you have a whole bunch of Python modules installed into your home and you don't want to utilize those Python modules, but you want to use different Python modules. This is one of those places or one of those options that will basically allow you to bend the rules of the universe a little bit. Singularity exec clean env. By default, all environment variables from your host shell are passed directly through into your container. Clean env basically cleans all of those out and gives you an absolute minimal environment or a clean environment. If you want to transpose environment variables, you can do so using the Singularity env underscore prefix to any environment variable, and that will get transposed inside the container. So Singularity env underscore hello will then become just hello inside the container. Let's see, Singularity exec. You can run, so Singularity exec, sorry, Singularity exec Python, and then point it to a Python script in your current directory. Obviously will run, considering that file is available, but you can also cat that script into Singularity and then exec Python. So you can actually run the program through a pipe. So inside the container, we'll basically be able to receive standard in. And lastly, how do you run an MPI program through Singularity? In this case, you're basically doing a Singularity, MPI, Singularity exec, point at the container, and then you're going to point it to the path of the MPI program that exists inside the container. And here's an example of what that looks like. So basically, it looks exactly as it would look like if you just ran this directly on the host. Now, running it like this is very important, because if you've been doing MPI on a shared HPC resource, you probably already know that there is a relationship between the resource manager and the host-based MPI. Notice, for example, I didn't pass any arguments to the MPI run. I didn't have to tell it how many processes to run, what nodes to run it on, or anything like that. That's because the resource manager has communicated this properly to the MPI run. If I don't run this MPI on the outside of the container, I don't have any way of knowing how many processes I should be running, where the resource manager is, how many nodes I'm running on. So this gives that this provides for the appropriate relationship that the system was built for. So starting off with running that MPI, the program that MPI run is going to run is a Singularity program. We're going to run Singularity exec pointing at the container, and then we're going to exec inside the container the MPI program that you want to run. Now, what's going to end up happening on the back end? Again, I'm going to get a little technical on this because I heard that there was some MPI questions. So I'm going to get a little technical on this. The MPI, and I should also mention, I'm going to assume Open MPI because that's what I'm most familiar with. So MPI run is going to fork the appropriate number of times it needs to satisfy the host requirement for every MPI job. So let's say, for example, we're running a four node MPI job, and each MPI on each host is basically going to be spinning up, let's just say 20 containers. That means it's going to fork 20 times. MPI run will. MPI run then will then call, excuse me, I actually backed up a little bit. MPI run will first fork an ORTED process. ORTED will fork 20 times. The ORTED process then will exec, each one of those 20 will exec into Singularity. Singularity then will set up the container and then exec into MPI, exec into the MPI ring program. The MPI ring program in this case will link to the MPI libraries that exist inside the container. Those MPI libraries that exist inside the container need to reach back out and contact their associated ORTED processes to basically complete the communication loop. And it does so right through Singularity. So basically, those libraries inside the container are going to reach back out and call the original MPI run or the original ORTED process. And it will do that over something called the Process Management Interface, or PMI. That now completes the loop. Now remember, Singularity has execed itself out of existence. So from the MPI perspective, we have an MPI run who forked and execed an ORTED process. The ORTED process forked and execed each one of these MPI programs. And these MPI programs linked to their libraries, which then communicated back to the ORTED process. The long story short here is that the MPI is running exactly the way it's designed to run. Granted, we've injected a little bit of stuff right in the middle of its process, but we're running right from the resource manager to the calling host's MPI, all the way through the container, and then back to the calling MPI. So we've completed the loop exactly as it's designed to run. And that's the big take-home message here. And there are multiple MPIs that work in this fashion. So far, we've tested and have good results from Open MPI, as I mentioned, MPitch, MVAPitch, the Intel MPI. I believe there's another even that I'm forgetting. Yeah, I'm forgetting. I'm sorry. But you can see that basically we've had interactions both with the developers of these other MPIs, and we've worked with them to get testing, to get qualification, and to make sure everything's working properly. Ironically, don't mention this to the Open MPI people, and if there's any in there, I apologize, but Open MPI was the most difficult to get running and get debugged. All of the other MPIs worked without any modifications. All right. So let's move on. Speaking about Open MPI, here's a bootstrap definition that talks about how to create this is a Yum-based bootstrap. So this is a rel compatible container. And basically what we're going to do, we're basically going to install the Yum group development tools. We're going to then do a git clone of OpenMPI. We're going to do an autogen configure, make install, and then we exit out. And the reason why I put this in here is not because I think that this is a good example of something you should do in a container, because it's not reproducible, because we're pulling out of Git, but because I wanted to demonstrate how you can use the PostScriptlet to do different types of things. So this one's basically pulling out of Git and doing, a build from Git master. Here's what something would look like from OpenFOAM. This time we're going to use a Debian-based container. And in the post, we're going to do some apt-gets, and then we're going to basically do a wget and pull the key, add in a repository, and then do an apt-get install for OpenFOAM 4. TensorFlow is somewhat similar. Okay, so let's play a little bit with Python versions. I'm assuming most people here are somewhat familiar with Python. So if we do a Python hello.py, in this hello.py, it's not just a hello world script, it also prints out what version of Python we're running. In the host, you can see I'm running 2.7.6. If I do a Singularity exec pointed at the latest version of Python that exists in Docker Hub, you'll see now, after some generic output of what Singularity is doing, we're running on 3.6.1. And if I cat my hello world script and then run it through Python 2 that exists in Docker Hub, you'll see now I'm running on 2.7.13. So incredibly easily, we can change our version of Python and test against different versions of Python. If we want to pull a Python container, or rather create a container from Docker Hub, you can use the pull command, Singularity pull pointed at Docker. It'll create a new image and fill it up automatically with what's inside of Docker Hub. You can also then basically do exactly the same thing. You can run Python latest pointed at the image, and you can see now we're running 3.6.1. Like I mentioned earlier, you could take that image and put it in user local bin, or even just user bin, or wherever you want. And then you can run that directly. You can even put that as the interpreter of your script, and it will work appropriately. Okay. I want to talk about Intel Python a little bit. You can utilize Intel Python just by basically pulling the container, as you can see, using the same method we just demonstrated. We can then exec into that. You can see we're running now Intel's version of Python, or we can run against Intel Python 2, or you can bootstrap Intel Python, again, using the same sort of method. And again, this is what it would look like if you basically build the container from scratch. And if you want to use the container again, temp Intel Python.image, give it the version. You can see that's the version it's running. You can point it to the hello world script that I created earlier, or you can run it interactively. The point is that it's running exactly as it would as if it were a standalone program on your system. Here's an example using GPU support with TensorFlow. So on the host, we have the NVIDIA CUDA libraries and kernel modules already installed by the system administrator. So now we can just do a Singularity run, specify we want to use the NVIDIA module for Singularity, and then point it at the latest version of TensorFlow that enables GPU support. And it will basically go through, it'll download all those layers, and it'll spin up a Jupyter notebook, or Jupyter Hub notebook, and basically then give you a URL in which you can paste into your local browser and then get access to a GPU-enabled version of TensorFlow through Jupyter Hub. Quick demonstration of some of the performance of I/O on various applications. The take-home message here is that green is native, blue is Singularity, red is Docker. For the most part, all of these are pretty close. There's some applications that do things a little bit differently and create a little bit more of a divergence. But for the most part, you're going to see it goes green, blue, red. Native, Singularity, and then Docker. This is shared memory latency between containers. And again, you're going to see that the line and the curve pretty much follows identically. There's not too many data points on here. but you will see this trend, and you'll be able to reproduce this trend fairly easily. This is one of the reasons, by the way, that we don't separate out all of the namespaces. If we did separate out the namespaces, all of them, for example, in this particular case, the PID namespace and the IPC namespace, what you would see is that the process would degrade very quickly, because we no longer can do shared memory between containers. But Singularity allows shared memory between containers. This is containerized MPI latency, a quick comparison. In this case, we're not even seeing the effects of the container. What we're actually seeing is the effects of the fact that the libraries in CentOS 7.2 are less efficient than what you see in 7.3 or in Ubuntu. So the fact that we can even run on 7.2, CentOS 7.2, which is native, and then run a 7.3 user space, we're actually seeing a performance speed up through Singularity. Now, I don't want to mislead anyone. These graphs are showing the deltas between. They're not the full graphs, obviously. You're not going to see, that much of a performance delta. So make sure you look at the y-axis. And you see the same thing both with latency and with bandwidth. You see higher performance with the newer libraries in the user space. Another quote, University of Cape Town in South Africa. This is a brilliant containerization technology which will gain traction very quickly. So with that, let's jump into some use cases. So Lawrence Berkeley Labs and UC Berkeley, we use Singularity to primarily support the long tail of science. Now, the long tail of science is basically considered the non-traditional HPC scientific job. And this allows us to get a much wider breadth of support of science on our systems. And we're seeing everything from not just the traditional science using Singularity containers, but we're also seeing things like political science, library sciences, things that we never would have really imagined, humanities that are actually now being able to use computational resources, high-performance computing computational resources for their own workflows. And additionally, we've been able to resurrect from the grave some workflows that we thought were going to be lost. And this is an interesting example. I also heard that there was a question regarding, what is the container reproducibility as a function of time? Long amount of time, like 10 years. So I'll go past that. So we had a system that used to be running Red Hat Linux 8. I could see some of you. Quick show of hands. How many people here actually used Red Hat Linux before it was Enterprise Linux? Okay, some of you guys. So Red Hat Linux 8 is ancient. I mean, this was in 2002. So we had a system that was basically built in 2002. We had a postdoc came and wrote a bunch of code on that, using some libraries again that were specific to Red Hat Linux 8, and that system has been running in production for approximately 15 years. And then that hardware decided to stop working. Now, unfortunately, the scientists stopped thinking about this because, well, it's working, it's been working, it's going to work forever. So they just stopped thinking about that particular system and just used it as part of their workflow. The detector basically is coming off the detector. This is one of the systems in the pipeline that just had to work. Now, what ended up happening was, obviously, as we pretty much all know with common sense, when we're thinking about it at least, is that these systems don't last forever. They're not appliances. And what ended up happening is something went wrong on the system. They started getting all sorts of weird failures. Systems started booting, randomly and whatnot, and it started crashing pretty quick. We were able to get on there before the hard drive completely crashed, and pull the contents of that hard drive and put it into a Singularity image. And now we have that 15-year-old system image running on the latest version of CentOS within a supported environment. So we're actually running a 15-year-old operating system inside of a container, and it's working fine. Those scientists are continuing with their workflow. Now, this also demonstrates a very good thing, obviously, but it's also kind of a bad thing, which is you don't necessarily want to use this as an excuse for not maintaining code, right? But a lot of times the way that the funding or grants are designed, it's not always possible to maintain the code, or at least do active maintenance, proactive active maintenance, because you don't have funding for that. A lot of the funding basically comes in first year, you develop your code, and the next year you're basically running the code. So if possible, obviously you always want to be maintaining your code, but if that's not an option, it's good to know that you can always come back and kind of rely on a container to do this sort of a thing for you. But it's also, it's a way of approximating what we're going to look like in the future. So I would feel very comfortable stating that if you have a Singularity container now, I would say you have at least 10 years of good use of that container, where that container is going to be operational within a Singularity container. So it's a function of about 10, maybe more years, but I would feel comfortable saying 10 for sure. All right. There's a workflow management language called Nextflow. Do we have any Nextflow users in the room? Okay, well, if not, you should definitely check it out. Nextflow basically uses Singularity to deploy large-scale distributed scientific workflows, commonly used in genomics pipelines, and it easily makes use of both HPC cluster as well as cloud technologies in a portable manner. And here are some of the examples of users that are currently using it. The NIH uses Singularity to provide programs like TensorFlow, OpenCV3 and whatnot, or which are difficult to and are impossible to run on their current operating system. With Singularity, they can also create portable, reproducible data analysis pipelines, and it allows them to do this in a somewhat secure environment. System admins have found it easy and intuitive to use, and some applications have been installed into Singularity containers and uses standalone programs via environment modules for the user. So this is what I was talking about earlier, being that you can have a container that runs like a standard program. University of Cape Town, this is one I just heard of recently. Among the standard HPC use cases, they're basically using, their researchers use a lot of IPython notebooks via Jupyter Hub. We show of hands, Jupyter Hub users. Okay, you guys should probably check out Jupyter Hub as well if you're not already. But IPython Jupyter Hub kernels were deployed in Singularity containers. So the kernels themselves that the users are using from the web interface from Jupyter Hub are actually now containerized automatically just because they happen to be running inside of the Singularity object. Once the container is deployed via Jupyter Hub, the user's jobs now are running within the container while they can maintain the access to the local node resources. And this is a multi-user environment. And so Docker is a non-starter. Again, if you're familiar with Docker, you're probably familiar why you can't run multiple jobs on a single node as multiple different users with the same container. Who owns the resulting data? Yeah. GSI, Center for Ion Research. Alice jobs are packed into Singularity containers, and then the jobs are executed via a modified Slurm script through Singularity. And at any given moment in time, there are about 2,000 Singularity containers active on the system. I believe Michael already used this example. And Michael that you have there is the standing expert there. So feel free to ask him lots more questions if you haven't already. The Open Science Grid. The Open Science Grid uses Singularity to provide consistent runtime environments across heterogeneous resources worldwide, and container images are distributed via the CERN file system to all sites. And they're approximating at current, there's about 500,000 jobs are run through Singularity per day. Now, where are we? Current status. Current status is version 2.3.1. We have a paper. It's been published at PLOS. Growth has been really, really hard to keep up with. There's been massive uptake within the world, within the HPC community. And as a result, I kind of explained SingularityWare a little bit earlier, and it's been created basically to help bridge the OSS community to industry and help fund development. Singularity will remain now, and as always, open source BSD 3-clause license. And aside from having money for development, and growing more, nothing else is changing. If people have been watching, I used to work primarily for Lawrence Berkeley National Lab. And now I'm doing multiple things. So I just wanted to set everybody's mind at ease. Nothing is changing aside from the fact that we have the ability now to develop Singularity more aggressively. I'm hiring if you are an awesome person with C knowledge, kernel, security, anything like that. Or if you know anyone like that, please send me your resume. And a couple things of what's coming soon. Concept of data containers. These are, like I was talking about earlier about bind points onto the host. These are bind points into additional container images. This gives you the ability to separate out your contained data from your contained runtime operating system. And specifically, this gives the ability to interoperate with object stores very easily. So a lot of people are using object stores nowadays, but object stores typically are using a REST interface, a REST API. And so unless you're going to code your application to obtain your code or obtain your data from these REST APIs, download it locally, and then use local storage to interact with it and then push it back, it's a little bit difficult to deal with. So in many cases, data containers are going to end up being a very nice solution to this. And again, they work fantastic for consolidation of large numbers of small files. And it allows you, again, to use an object store while maintaining POSIX-based I/O. So if you're doing things like open, you're doing writes, you're doing, fopen, anything like that inside of your code, those are all POSIX-based system calls. So you're going to need local file system access. So this will give you that ability, so you don't have to change your source code. Now, I'm hoping everybody here has heard of research data management and the RDM problems associated with. So we're also looking into working with RDM and to ensure that scientific data and runtimes can be both managed in an RDM world. So as I mentioned, everybody in science is pretty much looking for an RDM solution right now. And it's commonplace that RDM is starting to become a requirement in many grants, funding grants, and allocations. And we, in Singularity Ware, and we're basically working on this with a very strategic partner. And I will give a hint here. That strategic partner is RStore, so which I'm a senior architect at. And so hopefully we're going to be helping to solve this problem. And with Singularity and a RDM solution, you can then deal with your containers as you would any other piece of your scientific data. This again allows you to utilize the runtime environment container, then just becomes a component of your research and your data management plans. And the use case here is pretty much all scientific institutions everywhere. Everybody needs this. All right, trusted computing. The idea of trusted computing is that you can appropriately verify the environment that you're running in. Seems like a pretty easy thing to do, but it's not. And one thing about Singularity's architecture and the fact that it's distributing single image containers means we're very uniquely optimized throughout the container ecosystem of tools to do this. We can do very easy verification because we are a single file. There's a lot of pluses and minuses of the entire environment being a single file. And because I'm biased, I'm not going to tell you any of the negative associations to it, but I can tell you a lot of the positive ones. And the positive ones are things like you can checksum. You can, if you're more paranoid, you can do things like TPM-based verification of that image, which will actually do a signature check against the processor and the actual physical hardware. So you actually can bypass your operating system. And additionally, you can do a check of your container from within the container. So if you have a particular application itself that you want to do a TPM verification of, you can actually have that application reach back out through an open file descriptor that we're handing to the container runtime to see what is that container. And you can actually then do your own check on it from within the container. And the use cases here are highly secure environments, medical, government, finance, and enterprise. Another feature that's going to be coming soon is the optimized image format. At present, Singularity, the Singularity image format is basically an embedded POSIX file system. This is why we needed pseudo in some of those earlier cases, or one of the reasons why we needed pseudo in some of those earlier cases for doing things like Bootstrap. But the image is basically a POSIX image or POSIX file system with an header and an offset. And this forces that we have to maintain POSIX semantics everywhere. Even when it's not necessary. I mean, in a contained environment, we don't always need to maintain POSIX semantics, but we do because we're based on a POSIX file system. And it also means we have to deal with static image sizes. So Singularity v3, which is going to be the demarcation for a new image format, it's probably about a year out. It will support its own image file system, and it will be designed specifically for the agile trusted container usage. And when I say agile, I mean highly mobile. You can take this container image anywhere again. And again, focused on trusted container, trusted compute as well. This will give us the ability to do more things without privilege and, of course, support more features. Another feature that's going to be coming soon, this is going to be coming much sooner than the new file system image format, is the daemonized and background process support. This basically gives us the ability to join and leave container namespaces. There'll be a Singularity init process, which will manage the container's PID and the network namespace. And parent-child relationships will always be maintained. Again, so we're going to be compatible with resource managers. And new Singularity verbs will be introduced, like start, stop, and status. And here's a quick example of it. You can do a Singularity start container image. You can check the status of that image. And then you can exec something like HTTPD inside that container image. And then via a follow-up command, you can see that that HTTPD process is actually running. I believe Michael mentioned this and talked a little bit about this in the earlier presentation. Another feature that's going to be coming soon is orchestration support. So one of the most utilized things is basically how do we orchestrate with things like Kubernetes and Mesos, and how do we work with that? So we've been funded by an outside entity in the U.S. government to basically specifically support this use case. And the idea is basically to deploy Kubernetes services via Singularity and then utilize the new start-stop functionality that Michael is working on. And use cases, again, cloud-based science, high throughput computing, serial computing, et cetera, and so forth. Quick list of the universities that have contributed code. Now, these are not the users. Of course, they are users as well. I mean, the users are much larger. We have a lot more users out there in the world. But these are the people that have actually contributed code and resources to the Singularity project. The reason why I demonstrate this and I show this is because the project has grown, I mean, massively. Remember, this project is just over a year old. So the uptake has been fantastic. If you want to get access to Singularity, you can check out the homepage or the GitHub. I'm not a huge Twitterer. Is that a word? Tweeter. I'm not a huge that just sounds weird. Whatever. I'm not a huge user of Twitter, but you can follow here, and I typically repost what people are doing with Singularity and post announcements and stuff like that. And additionally, there's a Slack team. So if anybody wants to join the Slack, send me email. And my email is listed at the bottom of this page. So if anybody has any questions, please feel free to email me directly. Michael's also over there, and he can invite people to the Singularity Slack as well. So if you wish to just give him your email address while you're there, please do so. I'm volunteering you for a whole bunch of things, Michael. Sorry. All right. And so with that, I will open up to questions.